Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about some properties of the mean. The goal is to cover some important properties of the mean of a random variable. The prerequisites are independence of random variables and the mean. Let's begin with an example. We're going to determine the mean cost of a latte within a model where the price per kilogram of coffee is represented by a random variable C that has mean 2.5, and the price per gallon of milk is represented by a random variable M with mean 3.5. C and M are not independent. We're not going to assume independence here. And now we want to know what's the mean cost of a latte if a latte has 0.02 kilograms of coffee and 0.1 gallons of milk. Hopefully that is more or less realistic because I'm not a big coffee drinker. Okay, so what is the mean cost of a latte within this model? So let's see. We want the mean of 0.02c plus 0.1m, and we write it out as this function of C and M times the joint PDF integrated over all possible values of C and M. And now we realize that because of linearity of integrals, and let's see what I mean by linearity of integrals. So first of all, we have a sum here. When we have the integral of a sum is just equal to the sum of the integrals. So I can separate that. And when I have a constant inside the integral, the constant can come out of the integral. So now I end up with an expression. Let me erase this because it might be a bit distracting. I have an expression where here have one part of the function that we're interested in. Here I have the other part of the function. And the constants have come out of the integral. So this is just equal to 0.02, and now this is just the expectation of this function, right? Because it's this function of C and M times the joint. So this is just E of C plus that constant, the expected value of M in this case, right? This is another function of C and M that is multiplied by the joint PDF. So we have this equality. And this is always going to happen when we have a sum and some constants because of linearity of integrals. It would be exactly the same thing if we were taking the expected value of the sum of discrete random variables, because the sum is also linear. Here it turns out also, by the way, that since this only depends on C and this only depends on M, we can integrate over the other variable to compute the marginal, but that's not super important. The important thing is that we end up with this constant times expected value of one of the terms plus this constant times expected value of this other term. And in general, and the result is 40 cents. That's the mean cost of a latte. I would actually be curious to know what the actual mean cost of a latte is. I mean, okay, if you're in Manhattan, probably you also need to take into account how much you're paying for rent. Not only in Manhattan, you would also have to take into account how much you're paying the waiters and so on. Maybe this is a latte that you make at home. Okay, I'll stop rambling and continue talking about probability. Anyways, the point is that we have shown that because of linearity of integrals, if we have any constant C1 and C2 and any function G1 and G2, and we compute the expected value of this constant times the first function plus another constant times the second function, we can always split up this expected value or this mean into the sum of the two terms and bring the constants out. We would have been able to do exactly the same thing if we had discrete random variables, because sums are also discrete. This is called linearity of expectation, and it's super important. We use it all over the place when we manipulate expectation or expected values or means. Let me give you an example. You want to compute the mean of a binomial random variable A with parameters n and theta. You write down the sum of the PMF of the binomial, and you're like, oh, there's this binomial coefficient. I need to sum. This looks very, very complicated. But then you realize that you can actually write a binomial as a sum of Bernoulli, right? Because Bernoulli random variables are equal to 0 or 1, right? With parameter theta. And if you remember, a binomial is how many of n of them that are independent are equal to 1. So that's just their sum, right? So you can say that the binomial is just equal to the sum of these n Bernoulli random variables. And now you don't have to worry about, like this weird PMF of the binomial. You just say linearity of expectation. I'm going to get the sum outside. I know that the mean of a Bernoulli is just equal to this parameter. This is just equal to n times theta. That's it, mean of a binomial. So linearity of expectation can be extremely useful, as this illustrates, to simplify computations of expectations when you don't want to derive the distributions of the corresponding random variables. Have we used independence here, by the way? Okay, think about it. We have not. So we have shown that when you're flipping a coin, even if the flips are not independent, the mean number of flips that are going to be equal to 1, okay, as long as each flip has probability theta, is actually going to be n times theta, even if the flips are dependent, which is kind of interesting. Definitely when they're independent and you have a binomial. Okay, so this is a binomial with parameter n equals 20 and theta equals to 0.5, and this is the mean, which is right in the middle. Okay, so now let's go on to the other important property of the expected value or the mean that we're covering today. Imagine that you have a function, you want to know the expected value of this function of two random variables a and b. And it turns out that the function factorizes in a part that only depends on a and a part that only depends on b. And also a and b are independent, which means that g of a and h of b are also independent. Okay, so what happens here? We're going to go through the reasoning for continuous random variables. For discrete random variables, it's going to be super similar, except that here you would have sums. All right, so we have our function of interest. We multiply by the joint. But now we realize that the joint splits if the random variables are independent, right? It splits into a product of the marginals. So if we do that, this splits into a product of the marginals, we can actually separate the integral, and we would be able to separate a sum in the same way into a part that only depends on a and a part that only depends on b. And what is this? This is just the expected value of g of a, and this is the expected value of h of b. So this shows that when you have a product of two random variables or functions of random variables that are independent and you want the mean value, it's going to factorize into the product of the mean values. And the same for discrete random variables, because, like the sums would, I just explained, right? You would get exactly the same result. However, here, I do want to say, for linearity of expectation, I emphasize that we were not using independence. Here, we absolutely are using independence. In order to show you that independence is completely necessary in this case, let me go through an example. So in this hypothetical situation, you want to estimate the expected revenue of a restaurant. You see that the mean number of customers is 50. The mean amount spent per customer is about $40. Maybe you gather some data. And then you would expect the mean revenue probably to be $2,000, right? But you realize it's not. So the owner of the restaurant tells you, like, hey, what's going on? I don't understand this. Like, we have a mean number of customers that is equal to 40, so on average we have 50 customers. On average, they spend $40. Why is our mean revenue not 2,000? I don't understand. Something weird's going on. Tell me about it, since you're a data scientist. Okay, so what do? You explain that what happens here is that you don't necessarily have independence, right? Like if you don't have independence, then you cannot just say that the mean revenue is equal to the mean number of customers multiplied by the mean amount of dollars spent per customer. That's just not how it works. And we can actually provide an example that really shows that this is the case. Imagine that this restaurant, okay, this is a very specific example to make computations easy, but let's imagine that this restaurant has either busy nights or calm nights, okay? So, and the probability is 1/2. Usually, probably the calm nights would be during the week, and the busy nights would be in the weekend. Maybe I should have taking that into account. So maybe Friday, Saturday would be the busy nights. Maybe the rest of the nights would be calm. Anyways, here I've made our lives easy. I just said half-half. That's it. On busy nights, we get 80 customers who spend a lot. I don't know, they get drunk, things get a little bit crazy. They spend $60 each. On calm nights, people maybe are, more conservative. They're taking it easy. Maybe it's during the week. They don't want to spend too much. They only spend $20 each. So now let's compute. Let's compute the mean of the revenue. So the mean number of customers here, what is it? Well, we have 80 with probability 1/2, 20 with probability 1/2. We just sum them together. We get 100. We divide by 2, 50. Okay, so the mean number of customers is 50. What is the mean number of dollars spent per customer? So with probability 1/2, they spend $60. With probability 1/2, they spend $20. The mean is 40. Okay. But now, what is the mean revenue that we get? To compute the mean revenue, we need to compute the mean of the product. With probability 1/2, the mean revenue is 80 times 60. With probability 1/2, with probability 1/2, the revenue is 80 times 60. With probability 1/2, the revenue is 20 times 20. Okay, the calm nights. So this is equal to 400, and this is equal to 2400 if I'm not mistaken, which I often am. Actually, I am mistaken, right? Of course, that's not equal to 2400. That's equal to 4800. I somehow knew I would get it wrong. So this is equal to 5200 divided by 2, so that the mean revenue is 2600. So what is happening? Precisely when you have a lot of customers, they also spend more. So this gets amplified when you multiply them, right? When you multiply both numbers, so you have to be very careful. An expected value or the mean is going to factorize into a product of expected values, but only under independence. If you don't have independence, then this won't be the case anymore. Okay, as exemplified by this, as illustrated by this example. So what have we learned? We have learned that the mean or expected value is always linear, no matter whether things are independent or not. We have also learned that under independence, the mean or expected value factorizes into a product of means, but this only happens under independence. Thank you very much.